Well, I got tired of second guessing myself, so I decided to sit down this morning and get the schematic and go through and just take a whole bunch of notes and kind of mark them all over the schematic. All the voltages, all the functions. I went through and I got the good working amplifier, took a whole bunch of voltage measurements, and then marked it down on the schematic. And again, these voltages aren't exact, but they're in the ballpark of where they should be. And one thing I did prove 100% is the service manual is incorrect. So they're saying that B plus and B minus are measured with respect to ground bus, but the transistor voltages are measured with respect to B minus. Now that is impossible. Actually, what this should say is that all transistor voltages are measured with respect to ground bus as well. I'm not sure why they put that statement in there, because that will really throw you off. These voltages are somewhat correct if you measure them with respect to actual ground bus. And one example, for instance, what they're saying is they want, somewhere around negative 41 volts here and negative 41 volts here. Well, it's deriving its power from the B minus. So if you reference it to B minus, then obviously you can't measure minus 41 volts from B minus to this area. It's just not going to happen. So it just doesn't make any sense on many levels. So that was something to look at. So here's where we are right now. These voltages all here were kind of completely whacked out. This transistor was running warm, very warm. And these voltages out here were definitely wrong. Nothing here seemed to be bad on the surface, but then when we pulled this I believe it was Q112 transistor out, it was shorted. And after further investigation, I figured, I went through the process of replacing this, but then I pulled Q108 and Q111, these two here. This is Q108 that's in here right now. And yep, it's bad. It has an open circuit between base and collector. So, well, it's bad as well. So we're going to have to replace the drivers. So we ended up replacing the drivers and having to replace the current limit transistors. These are like kind of a protect circuit. It's an overcurrent protection circuit. Not unlike ones used in other amplifiers. It's just a little different way that they're deriving it. This works off the voltage drop across this CR109, which is controlled by this voltage drop here. And it will turn this thing on and off to kind of fold over this base voltage for your main output transistor. So once again, one of these was shorted and one of these was open. So we end up having to replace all of those little TO66 transistors with TO220s. Really, it helped a lot to get this schematic and put the notes on here, because then that's when you can actually follow through and check the voltages. And this is a really interesting circuit, and we'll talk a little more about how it works once we get this thing repaired and running. I still have not got this thing working properly, so we're going to replace those transistors, test it out, see if we have some success, and if we do, we'll go over some theory. All right, so the problem was our bias was all crazy. We couldn't adjust it. The DC balance was crazy. We couldn't adjust it. And all the voltages were completely wrong. And the negative side, your negative voltage side rail, was turned full on, just crazy. So again, we found those, one shorted and one open transistor. And Obviously, at the very beginning, when we first opened this amp up, the first thing we noticed was that same side, the light bulb had blown a filament. So probably something failed. Now, part of the problem is I take these things apart and I get called out. And I have to go out and do things or go to work or whatever, and then I come back and where did I leave off? So anyway, a little bit of confusion, and then to add insult to injury, there were some typos in the service manual, and we really needed to kind of get our mind wrapped around how this amp works. So that's where we are right now. So these two drive signals, which is this little pin here and this little pin here, represents your minus and positive drive here, and this is your bias circuit, your bias spreader circuit here in the middle. So what we really should see here is only about 1.5 volts or so, 1.25 volts, something like that on each one of these. But what we were getting was just crazy. You know, this was like 13 volts here, this was 40 volts here, something like that. It was way off. So, all right, enough talk. Let's plug it in and see what happens. I still have current limiting turned on, and here we go. Wait for our delay on time, and there it goes. We have about 1.2 volts, 1.18. And if we go over to the other side, 1.39. So it's out of balance a little bit. And if that is the case, what do we have on our speaker terminals? 100 millivolts on the speaker terminals. So we probably want to adjust that, or at least see if it will adjust. So let's turn this pot up here, and sure enough, now it works. Look at that. How's that for DC offset? 3 millivolts. I'll buy that for $1. And I'm sure we can mess around with this after it warms up a little bit and just kind of get it to... Look at that. Wow. That's what I call DC offset. Not even 1 millivolt. Okay, so that all said, I'm thinking this is good. Let's plug this in to our big power supply and put the full 120 volts to it, and we'll see how many watts we're getting. Okay, we have our 120 volts. Let's plug it in. That's start up, and boom, turns on. It's only running about half power. They want 30 watts at idle. So let's, I have my bias turned all the way down. Let's see if we can turn it up now. And sure enough, it is working. Look at that. Really touchy. 29.4, that's close enough. So we got our idle current. The amplifier is working. All right, let's unplug it. So I know I'm going to get comments about these transistors and they're not original and the amp's not going to work the same, but that is absolutely not true. These DTM11s and DTM12s, even though they're in a different case, this is an older case style, they actually are a pretty close match with the KSC 2073 and the KSA 940. Now, these transistors actually can handle more power than the originals a little bit, but when it comes to the rest of the characteristics, they spec up pretty close or better. So it will perform exactly the same way in there, even though it looks a little different. So I don't worry about what the case looks like. What's important is functionally it has to be exactly the same, or it will change the properties of the amp. Now, the same thing applies to these 2N5401s up here. These must be matched, a matched pair. The pair that was in there, at least the one that was good, was a gain at low, the HFE at low current was about 160. These are right around 165 each, and they're within a little, pretty close. VBE is almost identical on both of them. So this is a matched pair. This one was a little bit higher gain that I pulled out. I figured I'd replace it because it had already been worked on. I saw that. So I got one. It had an HFE of closer to 200, so I picked one that was like that, although I don't think it really matters on this one here, on this current source. And that brings us a little bit into this here, and kind of what's happening here. So this transistor up here is where it all begins. And if you look, this is actually setting up a constant current source for your differential pair down here. And it serves two purposes. Purpose number one is the current source, obviously. But purpose number two, if you look, you have your B minus, comes in, goes through this big 180K resistor. That's real high resistance. So you're really limiting current here. Goes up here, and it goes through this voltage divider network between the 100K and the 56K up to the B plus. So you're referencing this between B plus and B minus, which is a total of approximately 85 volts. And this diode here is clamping this so that you can't get that negative voltage. You can't flip this thing from positive voltage across it to negative voltage across it. That's what this thing does, this diode. This is actually an RC time constant. So as this 180K and this network begin to charge up this capacitor here, the drop between these two will eventually rise up until it comes up high enough to bias and turn on this constant current source. Once this constant current source turns on, that enables your first differential pair to come on. Now, why do we have a current source up here? Well, by regulating the current, remember, transistors are current devices. In other words, they work on current, whereas vacuum tubes work on voltage. You can read about that. There's a lot of that on the internet. But essentially, by not allowing these transistors to vary the current, you're essentially turning this into a voltage amplifier circuit. Because what we want to do is we want to bring the amplitude of the signal up at the very beginning of the amp. So you have a tiny little signal coming in here. It's usually 1 volt RMS to a couple volts RMS at the very, very most, at maximum signal. But it can be just millivolts RMS coming in here. Goes through this little network down here. You have a decoupling capacitor and a resistor, and it goes down here into the base of Q103, and this differential pair is actually going to act as a voltage amplifier circuit. Once it does that, it's actually going to adjust these two, which are current amplifiers. That's these two little transistors here. And it's limiting the drive signal between that you can have across here between these two by having these two back-to-back diodes. So the most you can ever have difference between these 2 points is the equivalent of 1 diode drop, or 0.6, 0.7 volts roughly. So this is just kind of a protection or a limiting circuit of its, rudimentary one of its own, because you don't need a whole lot of base voltage here to turn these on. These aren't really worried about changing the amplitude of the voltage as much as being able to handle the extra current to go to the next stage, which is going to be your drivers. So your drivers are here and here, and they're regulated by they're turned on by this little bias circuit here. And this bias circuit, and by the way, up here is like a phase inverter. All this does is it flips the phase 180 degrees for this side, and then it stays the same on this side so that you have your positive and negative going half cycle. You need that phase inversion to be able to do that. So we're shifting that reference up to that set point here in the middle. Kind of what we were talking about when we did the little video on the Class A and Class AB amplifier theory. So this actually sets your bias spread, which brings these transistors on just a little bit, because this is Class AB. Remember, we want to eliminate that crossover distortion, so that's what this does. Now, the interesting thing about all of this is you can see where they put a lot of provisions in here. Like, for instance, you can actually jumper another resistor across this 150 ohm resistor to get precisely 4 milliamps of current, because that's what they're running this on, is 4 milliamps of current. So this current source is a 4 milliamp current source, and if you don't quite have that, you set this by shunting a little bit on here, and you can crank this up a little tiny bit to get it where you need it. And then this whole network here is what maintains that current source. So if the voltage up here varies a little bit, this is just going to it's going to hold that current to whatever that 4 milliamps. And this is what tells it what current to hold it to. Now, another thing you have here is you have these trimmer resistors that you add in here. There's one here and there's one down here, and you adjust the value of those resistors to get your maximum amplitude to the rails. You want it to clip right below the rail voltage itself. That basically what they want is they want 18 volts roughly. So they want this, at this point, they want you to be able to get 18 volts right around it clipping before it clips, and negative 18 volts right around where it clips. This sets that for the positive 18 volt clipping. This sets it for the negative 18 volt clipping. Then these two transistors here, they just kind of stay out of the way and kind of pass the signal through to the outputs until when we exceed that range where we're going to hit that 18 volts, this is actually going to kind of start clamping off the input to this transistor down here, and this one's going to clamp off the input to this transistor up here to limit the current so that you can't get into an overcurrent situation. Even if you did get into an overcurrent situation, they put these light bulbs in here, and that was these bulbs that we were looking at. And it's just kind of a really unique way of limiting current. Then by having these big stud diodes, which are these big things here and here, you can kind of see the backs of them mounted to the chassis. Those, the purpose of them is to actually clip off any high frequency component to this. So if you have anything in the RF frequency range, it's going to get rid of that, but also it's going to make sure that at high frequencies, like at 20 kilohertz, it's going to keep that waveform smooth. Remember, diodes have a little bit of capacitance in them. So this is actually going to kind of smooth out your high frequency response to make it a little bit smoother and reduce the distortion at high frequencies. Then here, of course, you have your Zobel or Buchero cell, or whatever you want to call it. This is actually going to also eliminate high frequency oscillation. You don't want parasitic oscillation taking place in the amp. So that's kind of what this all does. So that's in a nutshell how this amp works. And as you saw, we got it working. All right, let me get my microphone on here. Okay, so we have this thing all put together. We got the dummy load connected to it. And as you saw in the last clip, we got the bias and the DC offset both adjusted. We have our 120 volt power supply to plug this into. And I was actually able to find some of these, which are the little pin type bulbs. They're 6.3 volts. And if you want to look at the part number, I hope you can see that. There we go. That's a pretty good view of it. You can stop the camera here, or the video right now, if you want to write that down. And I'll show you the little bulbs. These are original, and you can buy them at Jameco Electronics, JAMECO.com. And you can see that's where I found these ones, and here's the part number. And I'm pretty sure these are, if not the correct ones, they're very close to it. The only thing is there are little metal tabs that slide over these to clip them in, and I didn't have those. So all I did was I took a little plastic washer like this, and I just reamed out the hole so it would fit, and then I just put a little zip tie on the back side, and the front faceplate, when it goes on, will pretty much hold this in place, so it's not going to go anywhere. And that should do it. And I'm sure there's many other ways you can figure out how to fasten that in there, but there it is. So let's plug this in, and got our nice little power supply, or our little power indicator lights working. And let's get you onto the camera, or I'm sorry, onto the oscilloscope with the camera. And okay, so I have a 1 kilohertz tone, and I have a 1 volt peak to peak. Let me change that to 1 volt RMS. All right, we're set to 0.5 volt RMS going in at 1 kilohertz. Amplifier's turned on, and let's turn this on and see what we get. Well, so far so good. So with 0.5 volt in, we're getting about 15.5 watts out. So let's start turning the amplitude up. And very bad asymmetrical clipping. So let's turn this off. So we're close, but no cigar quite yet. So let's go in and find out why we're getting asymmetrical clipping. It's clipping on one side, but not the other. Okay, this is going to be kind of tough to see in here. And, well, first of all, let's look over here at the schematic. If you look, this is the current limiting circuit. And this will cause that clipping looking waveform that you see if this activates. And the way this partially activates is from this little circuit right in here. You have this Zener diode, which is a 4.7 volt Zener. And it sets up the whole circuit for this little fold-over circuit here, which is going to clip your outputs. And you have one up here. And of course, this is your positive voltage rail. And then you have one down here, which is your negative voltage rail. And if you look at this first one, it's kind of buried down here on this transistor. It goes from right here where your rail voltage is down onto that transistor. And if we test it, let's back up the camera a little bit. You can see right at about 15 MA or milliamps, you have your 4.7 volts, and that's kind of where it ends. And it goes from about 4.2 at 2 milliamps. So now let's move this one over to this diode right here. And of course, it's wired in the opposite direction because of the negative voltage rail. Do you see anything wrong with that? Yeah, that's a bad Zener diode. And most likely that diode got fried when that transistor in there actually shorted out. So, fortunately, I keep my feathers numbered for just such an occasion. And I just so happen to have So 3 left. But I actually have some 4.7 volt Zener diodes. So we're going to actually check these out and get these swapped out. I'm probably going to replace both of them, although this one's probably still good. But we'll just, while I'm in here, I might as well do it. Good grief, what else can we find wrong? Well, we have the offending Zener diode replaced. You can see just kind of here I used a red Teflon tubing instead of that rubber stuff they had, and there's the other one there. And here's the old ones. And although I think these were originally 1/2 watt, I actually found some 1 watt ones that tracked really closely, characteristic-wise, to the originals. So hopefully we won't have to mess around with these resistors, because what they want is, if you get asymmetrical clipping, when this is working properly, that is, you're supposed to shunt another resistor across these until you get symmetrical clipping. And hopefully we got everything close enough that this will be perfect. So let's go back over to our oscilloscope. And I can tell you I've spent an awful lot of time on this amp, a lot more than I ever dreamed I would. But hey, what are we going to do? Sometimes you run into that, huh? Very interesting. Now let's connect a signal to it. And we'll turn the amplifier on. And let's see what we get. How about that? Let's wait till it reads power-wise. 73.72 watts. And if I go up a little more, it just starts to clip. How about that? And that fixed it. Who would have ever thunk it? So let's just recap what all we found here. So if we go back to our little schematic, I'll back up the camera a little bit. So this 4 milliamp current source was kind of a little bit flaky. So we replaced these 3 transistors. Although these ones were still good, I matched a new pair and put a modern pair in there, because those little domed transistors kind of scare me. These were good. This was good. Everything else in here was good. We had a shorted, what did I say? Q108, I think it was. And we had an open, what did we have? Like a Q112, was it? I can't remember. But we had two bad TO66 transistors. And then this diode up here was bad, I believe. Was it? Which one was it? Actually, it was this one that was bad. And that was causing it to clip on the lower half. So this was only passing about 1 volt. And it should be 4.7 volts. So now it's correct. The amplifier is running cool. We have very close to our 30 watts up here. Sitting at 31 right now. It bounces around a little bit, but not too bad. And we have absolutely no DC offset. It's sitting at 0. I mean, it's, you know, within 1 milliamp, or 1 millivolt, I'm sorry. So I think we're ready to put this one together. Finally, how many times have I said that? But let's put it together and see what it does. All right, now that we got this thing working, and I did a little bit of testing on it, and it's pretty stable and working pretty well. Let's do something new that we haven't done on the channel yet. You know, we're always looking at different ways of testing amplifiers, huh? But honestly, my opinion still stands that no test is better than connecting an amplifier to your speakers and your audio source and listening to it. It's really, at the end of the day, what you like. But as a repair technician, when you're working on these amps for others, you really want to try to ensure that they're working to their peak performance so that it represents what the amplifier was really designed to do. So some of the tests that we do on this channel are designed to do that. No test can tell you everything, but each little test is another tool that you can keep in your toolbox to better assess what the amplifier is doing. So what I'm going to try right now is I have a little file up here in Audacity. Audacity is a freeware program. You've seen me use it before. Everybody uses it. It's very common. That you can use to capture and create and play back different waveforms or sounds. You can load music into it, all kinds of things. But what we're going to do with this in this instance is we actually have a special test tone. And this test tone is referred to as an intermodulation distortion standard test. There is a 60 hertz tone that you can see right here, and then there is a 7 kilohertz tone riding on it at a lower frequency, and they are actually sitting at a ratio of 4:1. So in other words, the 7 kilohertz tone is actually 1/4 of the amplitude of the 60 hertz tone. I hope that kind of makes sense to you. So just to repeat, the 60 hertz tone is 4 times the amplitude of the 7 kilohertz tone. That's kind of a standard that everybody uses. So let's put this back to the whole waveform there. And I have it set to play a loop. So all it's going to do is it's going to keep looping this waveform over and over again. And I've set the amplitude coming out of my sound card to just about drive this amp into distortion, but not quite. So in other words, it's going to run it at pretty high volume into the dummy load. And then we have the output of the dummy load connected to the oscilloscope. And let me move you over to that. And the oscilloscope we actually have set in FFT mode, or fast Fourier transform mode. Now, I'll move a couple of things around because I want you to kind of understand what we're looking at first before any of this will make sense. Now, some of you already know this and have done this before in some form or another, but for those of you who haven't, I'll kind of go through. So the first thing we want to do is we want to turn on FFT, or fast Fourier transform. And most modern digital oscilloscopes will have this function. Even the cheap little Handtech 6000 USB oscilloscope down here that I have actually can do this. Although the Tektronix has a little bit better resolution, a little bit lower noise floor and so forth. Now this by no means can come even anywhere near the performance of a true spectrum analyzer. Spectrum analyzers have special preamplifier circuitry in them that allows you to analyze very, very small amplitude signals, whereas an oscilloscope really can't do that. So there are limitations in using FFT on an oscilloscope. And you know, a lot of people discuss that online, you know, why do we even need spectrum analyzers anymore? Well, when you start working with radio and RF, there's no possible way you can use this on an oscilloscope, because oscilloscopes just don't go down that far in sensitivity. So that's a limitation. But for the audio bandwidth, you're looking at a loud, you know, high amplitude signal coming into a low impedance load. This will be just fine. We'll be able to use it. Now, the tone that we're going to be interested in is not the 60 hertz tone, but rather the 7 kilohertz tone. And that's what we want to observe on here. So the first thing you have to kind of understand is how FFT works. So if you look down here at the bottom of the screen, you can see there's a little bit of information here where it says math. And this, you have the red trace. I actually have the two channels, channel 1 and channel 2, turned off. So you're only seeing the FFT signal right now. And I'm looking at FFT through channel 1, if that makes sense. So you don't have to have channel 1's trace turned on. You just have to have the math monitoring the signal at channel 1, if that makes sense. And I have the FFT scale set to linear RMS rather than logarithmic. Okay, logarithmic would be like reading this out, the amplitude in decibels, and it just shows too much of a noise floor. So this is a little bit easier to look at. So you can see how nice and flat we have that. Now, scopes will usually auto scale themselves. So when you first apply a waveform to it, these things will change themselves, and you're going to have to manually go in with the vertical and horizontal adjustments, you know, for your scope to get this where you want it. The first thing I'm going to do is I'm going to close this way down. I'm going to go to about 1.25 kilohertz. Now, what does that mean? That means each graticule from here to here represents 1.25 kilohertz or 1250 hertz higher frequency. Okay, so for instance, all the way to the left is 0 hertz. This first graticule would be 1.25 kilohertz, 2.5 kilohertz. Does that make sense? 3.75 kilohertz, and so forth. So 7 kilohertz is going to be somewhere over in here. It's going to be about five, right after 5.5 graticules, roughly, is going to be 7 kilohertz. So we should, if we turn this waveform on right now, we should see a 7 kilohertz bump right around here somewhere. And you're going to see that this is right now set to 50 millivolts of amplitude per graticule or per division. And you're going to see that's going to auto scale itself. The scope just does that. You're going to have to manually go in, and you're going to have to adjust this knob to change the amplitude. This knob is the one that changes how many kilohertz per division horizontally it is. We'll look at that in a minute. So we're going to start this up and turn on the waveform. And you can see a little bump in there. Now the first thing we have to do, right there is the very beginning, and there's your 60 hertz fundamental. You can see it at the beginning, how much higher amplitude it is than this one. And we're going to put the edge of the waveform right against the edge of the screen like that, of the scale. So once again, like I said, just over 5.5 graticules, that right there represents your 7 kilohertz signal. Now the problem is, what we want to look at, there's not enough of it on the screen for us to really see it clearly. So the first thing we have to do is we have to increase the sensitivity of the scope. So all I'm going to do is I'm going to take this vertical amplitude knob, and I'm just going to change it till I get about 20 millivolts per division. So now, because what we're going to be looking at is the bottom of this waveform here in a minute. The next thing I want to do is get more resolution. I want to spread this signal out a little bit. So what I'm going to do is I'm going to change it to less hertz per division, if that makes sense. So now we're at 500 hertz per division. We're now at 250 hertz, and you can kind of see as the scale is changing, it's spreading out, it's moving our waveform. So we have to use our centering knob, our position knob, horizontal position, and we can go, the maximum this scope will do is 125 hertz per division. Now, you're now seeing a relatively big 7 kilohertz waveform. And that's your fundamental. And that 60 hertz, that's 4 times as high of amplitude, is going to interfere with this. And if there's a problem with your amplifier, if there's distortion in the amplifier, what you're going to see is you're going to see that the side bands here and here, you'll see these tiny little bumps here. Let's see if we can go a little more sensitivity. There, 2 millivolts per division. And you can see just the tiniest little bit of side bands. That's your intermodulation distortion. And you can see on this amplifier it's extraordinarily small. Now, I don't have the amplifier driven into clipping right now. I'm running probably about 50 watts into the dummy load right now. So I'm pushing the amp pretty hard, but I'm not pushing it till it's making those little current limiting light bulbs light up or anything like that. But this is one quick test you can do with if you have a computer with an output that you can connect to the input of your amplifier. And really all I'm doing is coming out of the computer's sound card and going right into the input of the amplifier. And then I'm adjusting the amplitude of the amplifier before clipping. So I'm pushing it pretty hard. So right now the amp's getting warm because I'm driving the crap out of it right now. But it's not getting hot, it's handling it. And it's handling it very well. Now if I turn this back off, you can see how it automatically changed the scale. And that's why you have to remember when you shut the signal off and you turn it back on, you'll have to readjust your vertical amplitude. It's just a function of the oscilloscope, what it does. So there's a way to check intermodulation distortion. So that's this worked. This is the first time I tried this little setup. I just was interested in seeing, because we also have Spectrum software that we can use with the sound card. But unfortunately, I have a really high-end audio interface down here that works through USB. And unfortunately, when that big power surge went through and it trashed the computer up here, which I had to replace the main board on it, and it trashed the little amplifier, and it trashed a whole bunch of other things, it also trashed this audio interface. So I'm going to have to get another one. And that's what led me to wonder if maybe I could do this with the FFT function on an oscilloscope. And sure enough, you can. Now, that's the industry standard way to do it. There are other different tests that people do for intermodulation distortion with different frequencies and amplitudes, but the 60 hertz and 7 kilohertz at a 4:1 ratio is the standard. And that's a way that you can view that. Now, of course, if you had a spectrum analyzer, an audio spectrum analyzer, which they do make such an animal, I don't know if they still make them, but HP made a really popular one, which I don't have, by the way. You can actually get the resolution even better and look at it even more closely than an oscilloscope with FFT mode. So anyway, I thought that'd be interesting for me to do and interesting for you to see. I hope you enjoyed that. Let's go on to some more of our more basic common tests. All right, let's do our 1 kilohertz sine wave test that we typically do. And we have the Keithley 2015 distortion analyzer set to THD mode. We have our watt meter calculator on here, and we have our actual display of the waveform. And I have the amplifier set to drive pretty much at its maximum output. So the little current limiting bulbs will be glowing a little bit, and we're going to be right around 65 watts per channel, or 65 watts of power output, which is pretty much the limit of what this thing was designed to do. Although I can actually drive it up in the 70 watt range and it'll still maintain relatively low distortion. So let's turn this on and take a quick look. You have to give it a second for the watt meter to calculate. And you can see we have 66.7 watts, so almost 67 watts. And look at our total harmonic distortion. Beautiful. And let me move you down here. I'll turn this thing back on. And you can look at what these bulbs do when you're driving the amp really hard. See them light up? And that's their whole purpose. They're actually limiting the current going into the amplifier. So, gives you a little bit of an idea of how those work. So, I know that one of the things that I scratched my head the first time I looked at this amp, because it's the first I've ever dealt with one of these or even seen one in person. And I thought, how in the heck are those light bulbs going to be in there and not cause distortion or any kind of problems? You know, how's it going to do that? But sure enough, you can see we were driving a nice clean 67 watts through this thing and extraordinarily low distortion, yet those bulbs were lighting up and doing their thing. So I think this is a really neat little design, and it's a neat little amplifier. Okay, the next thing we're going to do is our audio sweep test, and this is a test to make sure that when you apply an equal load, a non-reactive load across the speaker terminal. So in this case we're using an 8 ohm non-inductive, non-capacitive resistor. So it's a non-reactive load. Theoretically, if you feed the same signal amplitude in, you should get the same amplified signal amplitude out through, regardless of what frequency you're feeding into it. So whether you're driving 20 hertz or 20 kilohertz into the amplifier, it should amplify it exactly the same amount, regardless, exactly the same, there's my English, the same amount regardless of the frequency. It will always be the same amplification factor. So if we don't have that, then there is something in the circuitry of the amplifier that is reactive, and what it's doing is it's causing the amplifier not to amplify the same amount at certain frequencies, if that makes sense. So let's turn this on, and I just have the amplitude set so that it should stay between these two lines, and you can see just the tiniest little amount of shrinkage when you get up towards that 20 kilohertz range. But it's very flat. And again, there's special software and so forth if you have a good audio interface for your computer that you can actually plot curves and things, and I never get into that because it's just too much setup to do for all these things. You can test yourself into insanity if you really want to. But a few of these tests can actually tell us a lot about how the amplifier is functioning. So far so good. So I'm now running the amplifier with a 1 kilohertz tone, and I'm driving it at about half of its rated power, right around that 30 watt range, because this is a 60 watt amplifier. And no, I'm not going to get out my infrared camera. I can do that and set it up and all that, but you can pick these up relatively inexpensively at hardware stores or department stores. You can order them online, and it's just a basic test tool to check the infrared temperature signature of an object. So there's a little laser pointer, and wherever the laser pointer is, that's the general area that you're measuring. And it's just nice to be able to monitor the temperature of the two heat sinks. The idea is, if everything's balanced properly, both the PNP and NPN sides of the amplifier should run at relatively consistent temperatures to one another. So if we go to this side, I'm going to take a measurement right here, and it's about 100 degrees Fahrenheit, about 39 degrees C. And on this side, about 38.9 degrees C, which is, again, about 100 to 101 degrees Fahrenheit. So what that's telling me, and that you have to run the amplifier for several minutes to make sure it kind of gets to its equilibrium point. It's telling me that this amp is running in a very balanced manner. Again, we replaced transistors in this and we used modern substitutes. And this amplifier is a little bit more finicky than most transistor amplifiers in that when they built this amp, there were a lot of places where, if you notice, they had to adjust resistor values, or they even chose custom hand-picked transistors to work properly to make this thing work at its peak performance. So whenever you replace something in these amps, and I can tell you from experience, you want to make sure you have the correct components. And this amp is working exactly as it would have worked the day it was built. Even though the transistors physically on the outside look a little bit different package-wise, they are performing in the exact same manner. There I go again, exact same. The same manner as the other original transistors. So we've tested this amp pretty well. I've done a burn-in test on it. I've been just running it, and it is rock solid. So really all we need to do is we need to go over to the other amp over here, and I am going to replace those 4 or 5 capacitors just because we found that those ones were, a couple of them were high ESR, the other ones were still perfect. I'm just going to go ahead for future proofing. And then I'm going to do the same burn-in test on that amp to make sure that the transistors that are in there are okay. If they are, I'm going to leave them alone. They're fine. If I notice any kind of anomalies, then we'll go ahead and we'll replace whatever transistors we need. But those are very high quality transistors they used in this amp. And there's really no need to replace them unless they're problematic. And I really think the reason this amp failed was because it was probably abused. These amps are 60-watt amplifiers. When you try to run them, till your speakers explode and your ears bleed, you're going to expect problems to happen. And I've always been a strong proponent of, when you buy an amplifier, make sure the amplifier can handle the load that you're going to present to it. If you're going to put a great big set of speakers on it that are not very efficient and that have a really bad reactance curve based on the frequency, and then you want to run it at very high volume levels, don't buy a small amplifier to do that. That's why these work really well. Everybody talks about how they work with the Klipsch horns, and those are very highly efficient speakers, so they don't need anything more than a 60-watt amplifier, and they will get extraordinarily loud and shake the house with just that little bit of power. So this is a great amplifier for the older, more efficient speaker types. It probably will have a very clean sound signature. It'll sound a lot like the higher end vacuum tube amplifiers of that same era, with less heat, less energy, and really super good distortion characteristics, as we saw in our little tests. So let's get the other amp done, and then we'll put it all together and give it one final test. Well, I've been playing this amp for a couple hours now, and it's staying just absolutely nice and cool. The sound is really good on it. It's dead silent. There's no hum, no hiss, nothing. I'm actually pretty surprised how this thing performs. So, well, it's another one off the bench here. And now we know about the Model 15 Marantz. It's something I never worked with, and it was very interesting to find out how it worked. So I guess that's going to wrap up this video, and I'm sure it's going to be quite a mess because I shot it over multiple days. Sometimes I just barely get started on it and I'd get called off of it. So we'll see how the video turns out, but I hope you enjoy it. And as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll be seeing you real soon with a lot more projects coming up here. I have quite a few things to go on the bench, so I'll keep them coming. So have a great day, everybody, and we wish you well and see you soon. Bye-bye.